Hello students, welcome to the fifth lecture on particle physics. And in the fourth lecture, strange particles, what I had told you that strange particles are produced in pairs through strong interactions, and strong interaction time is of the order of 10 power minus 23 seconds, while these particles which are formed in the final state like K plus and sigma minus in the interaction of a pion with a proton, this K plus and sigma minus, they have a long, relatively longer lifetime of the order of picoseconds or nanoseconds, and therefore these particles were called strange particles, and these strange particles were assigned a strangeness quantum number, where we saw that for K plus and K0 the strangeness quantum number is plus 1, while for K minus and K0 bar the strangeness quantum number is minus 1. Similarly for lambda, sigma plus, sigma 0, sigma minus, etc., the particles which we will discuss, their strangeness quantum number is minus 1. And if we talk about the antiparticle of lambda 0, then that will be lambda 0 bar, and the strangeness quantum number of lambda 0 bar will be plus 1. Therefore, in a strong interaction process, strangeness is conserved, and therefore in the strong interaction, if the particles are produced, then it will always give the particles in pairs such that one will have strangeness plus 1 and another will have strangeness minus 1. Now let us take a few examples. For example, if you take lambda 0 decaying into p plus pi minus, then you see that strangeness quantum number for lambda 0 is minus 1, while proton and pion, they are non-strange particle. Therefore, while they are decaying, strangeness is not conserved, and that is why a new interaction was introduced, and that was called as weak interaction. Then what we argue that is strange particles in the strong interaction processes, they are formed in pairs, while when they decay via weak interaction, and because of that they have got a very longer lifetime, and they decay into, for example, non-strange particles like p plus pi minus. This 64% here represents that 64% of the time they decay into p plus pi minus, and 36% time of the time they decay into neutron and pi 0, because one has to conserve the charge also. Therefore, these particles overall should have charge 0, as lambda is a neutral particle. Similarly, if you look at sigma plus decay, then sigma plus decays to p plus pi 0. Almost 51, branching ratio is 51.6%, and here also you can see that sigma plus is decaying into non-strange particle, while strangeness quantum number for sigma plus is minus 1. Similarly, if we look at sigma minus, in this example, that is decaying into n plus pi minus, and this is happening almost 100% of the time. Therefore, almost 100% of the time, a sigma minus is decaying into neutron plus pi minus. Similarly, if we look at K plus, then a K plus is decaying into mu plus plus nu mu almost 64% of the time, and as you can see, strangeness quantum number is plus 1 for K plus, and there is no quantum number, strangeness quantum number for the leptons. These are mu plus and nu mu, they are the leptons. Therefore, there is no quantum number, strangeness quantum number for the leptons, but the strangeness quantum number is there for these strange particles which were formed in pairs in the strong interaction processes, and then they decay via weak interaction. Before going ahead, let me tell you that strange particles, initially they were found to form in pairs, and people argued that they are produced in strong interaction processes. But later it was found that They can also be produced in electromagnetic interaction processes, where they also conserve strangeness. That means they are produced in pairs. And then later it was found that they can, a strange particle, they can also be produced through weak interaction processes. And for example, a nu mu bar interacting with proton is giving me mu plus and a lambda particle. Now, this is this is a lepton, non-strange particle. This is a proton, which is a non-strange particle. This is a muon, a lepton, which is always strangeness 0. Therefore, here the strangeness is -1. Therefore, what we are finding out that in the weak interaction process, we can produce a strange particle, but that will be only one of its type, not in pairs like we have in the strong interaction and electromagnetic interaction processes. While in the weak interaction process, you can have, instead of lambda 0, you can have also sigma 0, or similarly you can talk about other particles in these processes, and people found that they were being produced through weak interaction process as well as, but all the time, no matter whether they are being produced through a strong interaction or electromagnetic interaction or weak interaction, they always decay via weak interaction process. They have a very long lifetime, which cannot be explained on the basis of strong interaction or electromagnetic interaction. They are explained on the basis of introducing a new interaction that we call as the weak interaction process. Now, when more experiments were done, is what it was found that not only we have lambda, or we have a sigma plus, sigma 0 or sigma minus, we have also cascade 0, we have cascade minus, we have omega minus. Now, these four were assigned strangeness -1. These two were assigned strangeness -2, while omega minus was assigned strangeness quantum number to be -3. Therefore, strangeness -1 is for lambda, sigma plus, sigma 0 and sigma minus. Strangeness -2 for cascade 0 and cascade minus, and for omega minus, strangeness is -3. Now we will see while discussing baryon number conservation that besides omega minus, there will be antiparticle of omega minus, and that we shall call it as omega minus bar. And charge of omega minus is negative here. Charge of omega minus bar will be positive. Strangeness of omega minus is -3. Strangeness of omega minus bar will be +3. Similarly, for cascade minus, the antiparticle of cascade minus is cascade minus bar, whose charge will be positive because the charge of antiparticle will be opposite to the charge of particle, and strangeness quantum number for this particle will be +2. Similarly, for sigma plus, the antiparticle is sigma plus bar. For sigma minus, the antiparticle is sigma minus bar. For sigma 0, the antiparticle is sigma 0 bar. For lambda 0, we have already discussed, the antiparticle is lambda 0 bar. Therefore, and strangeness quantum number for all these four is +1. Strangeness quantum number for cascade 0 bar and cascade minus bar is +2, and for omega minus bar, strangeness quantum number is +3. Therefore, strangeness quantum number, again, they have been put by hand to understand interactions, and what I am telling you that these particles were formed or can be formed or have been formed to be formed through a strong interaction, through electromagnetic interaction, as well as weak interaction processes, but they always decay via weak interaction process. For example, here I am showing that I am taking an example where an omega minus is decaying into cascade 0 and a pi minus, and then cascade 0 has a finite lifetime, that is decaying into lambda 0 and a pi 0, and then a lambda 0 has got a finite lifetime, this will decay into p plus pi minus, and this pi 0 will give rise to 2 photons, and this pi minus will decay again to mu minus plus nu bar. Therefore, an omega minus was formed which decayed into cascade 0 and pi minus, and then cascade 0 decayed into lambda 0 plus pi 0. Lambda 0 had a finite lifetime that decayed into p plus pi minus, and pi 0 to 2 photons in the final state. Therefore, mind it, here there is a catch that cascade 0 is decaying into lambda 0 pi 0 through weak interaction process. But pi 0 is decaying into 2 photons. Photons are the quanta of electromagnetic interaction. Therefore, pi 0 is decaying via electromagnetic interaction, and electromagnetic interaction time is of the order of 10 power minus 16 seconds. Therefore, lifetime of pi 0 will be of that order, while for lambda, the lifetime will be, as I have told you, of the order of nanoseconds or picoseconds, something like that. Okay, then we have that lambda 0 decaying into p plus pi minus, and like here, pi minus will decay into mu minus plus nu mu bar. The same fate will happen with this pi minus also. They have got a certain definite lifetime, and pi minus is also decaying via weak interaction to mu minus plus nu mu bar. Similarly, if we take another decay mode of omega minus, that is cascade minus and pi 0, then cascade minus, to conserve charge, it will decay into lambda 0 and pi minus, and then lambda 0 will again decay to p plus pi minus, and pi minus will decay into mu minus and nu mu bar, and pi 0 through electromagnetic interaction will decay into 2 photons, and photons can give rise to electron-positron pair. Therefore, this is how you will have many particles in the decay of an omega minus, or many particles in the decay of a cascade 0. Therefore, we have the strangeness, and as you can see, these are all the examples of decay of strange particles. And as you can see, strangeness quantum number for S is, or for omega minus, is minus 3, which is decaying into cascade 0 plus pi minus. Cascade 0 strangeness is minus 2, for pi minus strangeness is 0. Therefore, how much is the change in strangeness? Final strangeness minus initial strangeness. The net change in strangeness is plus 1. Or if you take initial minus final, it will be minus 1. Therefore, change in strangeness is either you can say it's to be plus 1 or is minus 1. Similarly, if I talk about cascade 0, this is changing into lambda 0 to pi 0. And as you can see, strangeness quantum number for cascade 0 is minus 2. For lambda 0, it is minus 1. For this is 0. Therefore, change in strangeness, final minus initial, either you say that it is plus 1 or it is minus 1. Similarly, when we go to lambda 0, decaying into, say, p plus pi minus, then strangeness is minus 1, this is 0. Therefore, delta S is either plus 1 or minus 1, depending upon whether you call final minus initial or you take initial minus final. But there is an important catch, and that we will discuss in the next class, that an omega minus is decaying into cascade 0 and pi minus. What is prohibiting it to decay into lambda plus pi minus, or what is prohibiting it to decay into sigma 0 and pi minus? That means a strangeness minus 3 particle is decaying into a strangeness minus 2 particle, but it is not decaying it into a strangeness minus 1 particle, whether it is a lambda 0 or sigma 0. Though the masses of lambda 0 and sigma 0, they are much smaller than the mass of cascade 0. And that means from phase space consideration, you have ample phase space available for lambda 0 and sigma 0 for the omega minus to decay. But it is preferring to decay into cascade 0. Similarly, we can talk about a cascade 0, that why not a cascade 0 is decaying into a neutron as I'm just giving you example that a cascade 0 is decaying into a lambda 0 and pi 0, delta S is equal to 1 or minus 1, whatever you can call. But phase space wise, this should decay into a neutron plus pi 0. But this has not been observed. Okay, this has not been observed. That means there is some physics, and that we shall discuss about, that is known by the name delta S delta Q rule. We shall talk about this delta S delta Q rule later in the lectures, but the important point that you can notice from this slide is that omega minus is decaying into a particle which is heavier than the other options available to it, but it is decaying into those particles where you have the net change in strangeness quantum number either plus, or say the mod of delta S is 1, and this mod of delta S is equal to 1 is an important point. We shall see that only those processes will be possible where we will apply delta S is equal to delta Q rule to see that if delta S is minus 2 or delta S is minus 3, for example, how we can have delta S is equal to minus 3? For example, if I take an omega minus that is decaying into n plus pi minus. Okay, and omega minus is decaying into n plus pi minus. The mass of this is more than 1680 MeV, say approximately 1680 MeV, while neutron's mass is 939.5 MeV. This mass is 140 MeV. Then why not nature allows an omega minus to decay into neutron plus pi minus, whereas it favors cascade 0 to pi minus, where cascade 0 is much heavier particle than the neutron. We shall talk about it, but this is an important catch which we will discuss, that strangeness minus 3 will decay into minus 2, minus 2 will decay into minus 1, minus 1 will decay into strangeness 0. Okay, that means always delta S will be, mod of delta S will be 1. Only those processes will be allowed. Mod of delta S equal to greater than equal to 2 will be prohibited, will not be allowed, or will be forbidden. Okay, therefore we shall talk about it, but the important catch is mod of delta S greater than equal to 2, these processes are forbidden, while allowed processes are where we have delta S is equal to plus minus 1, and cascades will decay into a lambda or sigma. A lambda or sigma will decay into nucleon epion, and an omega will decay into cascade and pi 0. Now, with this introduction of strange particles, let us put all the particles which we have discussed in the previous slides: proton, lambda. You can notice from here, proton, its antiparticle, antiproton; lambda, its antiparticle, anti-lambda; sigma, plus minus. I have told you the antiparticle of sigma plus is sigma plus bar, sigma minus is sigma minus bar. For similarly, we have lambda and lambda bar antiparticle. This bar is perhaps not very visible. This is lambda bar. Okay, this is antiparticle is lambda bar. And then in the standard model of particle physics, we assign all the particles which I have listed here, some of them, as baryon number equal to plus 1, and all the antiparticles as baryon number to be minus 1. Therefore, lambda bar has a baryon number minus 1, while lambda has a baryon number plus 1. While this lambda bar has strangeness quantum number plus 1, while lambda has a strangeness quantum number -1. Therefore, try to understand this. We are calling proton as a particle, neutron as a particle, lambda as a particle, sigma as a particle, cascade is a particle. Therefore, these are particles, and therefore they have been assigned baryon number as +1. When we were discussing the leptons in the previous lecture, then we had independent lepton number for the first generation, independent lepton number for the second generation, and the independent lepton number for the tauon family, that is the third generation. But here in this case, we will see that all the particles of this family which have got structure, they are fermions, they will be assigned a baryon number to be +1. Therefore, mind it, what I am telling you, that all those particles which have got a structure, which are not point particles, which are not fundamental particles, but they are fermions, we are calling it as baryons with baryon quantum number +1. They can be strange particle or non-strange particle. They can be proton or neutron or the resonances of these particles. And the anti-particles, anti-proton, anti-neutron, anti-lambda, anti-sigma, these will be called as anti-fermion, or then specifically, since they have got a structure, we will call them as anti-baryon, and we will assign, or we are assigning, quantum number -1 to them, Therefore, try to understand this. Baryon number +1 for the particles. Therefore, the important point is that fermions, particles which are fermions, which have got structure, we are calling as them as particles. And the examples are proton, neutron, lambda, sigma, cascade, omega, delta, those I will introduce as the resonances. These particles are baryons. They are made up of 3 quarks that we will see. While they can have different strangeness. These are non-strange particles. These are strangeness -1 particle. This is strangeness -2 particle. Then anti-fermion, plus they have got a structure, they will be called as anti-baryons. And all those anti-baryons will have baryon quantum number to be equal to -1. All those particles will have anti-baryon number as equal to -1. Therefore, anti-fermion which have got structure, they are anti-baryons, and this can be cascade bar, sigma bar, lambda bar, delta bar, proton, anti-proton, anti-neutron, etc., etc. Therefore, the important point is we have a baryon number from the standard model of particle physics to all the fermions having structure as +1, and all the anti-fermions having structure as -1, while we had all the fermions which were not participating in strong interaction, but they were fundamental particles, they were structureless, they were called as leptons, which we divided into 3 different generations. Therefore, what are leptons? They are those particles which are fermions, they are those particles which are structureless, they are those particles which do not participate in strong interaction. While baryons are also fermions, they have got structure and they also participate in strong interaction. They are made up of quarks, they are not point objects. Okay, therefore here we are talking about the particles which have been observed in nature, and these particles have got some charges. Like I have told you that if lambda is neutral, then its antiparticle will also be neutral. Both will have same lifetime and the same mass. While charge, since they are neutral, both will be have the neutral charges. Then there is an important catch, and that catch is, before I move ahead, let me just discuss it since it is there in the table as the magnetic moment. Now, if you recall the magnetic moment of the electron, this is EH cross upon twice Me. This we call it as one Bohr magneton. Now, if I ask you the question, what will be the magnetic moment of the proton? Then you will say that this will be with a negative sign because the charge of the electron is negative. Let me put it here, and I'm just saying that magnetic moment of the electron is one Bohr magneton. Positron will be one Bohr magneton. But for the proton, on this basis, you will say that mass of the electron will be replaced by mass of the proton, and therefore this will be H cross upon twice MP in that. Okay. And then this means that proton's mass is 1836 times more than the electron mass. As you can recall, proton mass is 938.2 here, and then MeV, electron mass is 0.5 MeV. Therefore, it is about 1836 times proton is more massive than electron. Then that means since it is coming in denominator, proton's magnetic moment should be 1836 times smaller than the magnetic moment of the electron. And that we call it as one nuclear magneton. When experimentally it was seen, it was measured, it was found that it is not 1 mu n, but rather this is 2.79 mu n, or just I can write down it 1 plus 1.79. This 1.79 is known as the anomalous magnetic moment of the proton, and this arises because of the structure of the proton. Similarly, if we talk about neutron, if you replace it for the neutron, the neutrons are the neutral part. Neutrons are the neutral particle. Therefore, it should not have a magnetic moment. But it has been measured that they have got a finite magnetic moment, and that is known as the anomalous magnetic moment. Anomalous means strange, different from the normal one. And this strange anomalous magnetic moment for the neutron or for the lambda particle or for the others or for the proton to be more than one nuclear magneton led people to think about the structure of the charge distribution inside these baryons and mesons, or in general I should say the charge distribution inside the hadrons, which led to the concept of normal magnetic moment and the anomalous magnetic moment. And this anomalous magnetic moment is known as the strange magnetic moment. Now, in my next class, I will first introduce about the baryon number conservation, and then I will come to the classification of conservation laws to exact and approximate. Therefore, let us stop here, and this is the expression which I will use tomorrow in the next class to understand that like we have lepton number conservation, here we have baryon number conservation. Thank you very much, and see you in the next class.